All right, lesson 6-5 is taking everything that we have learned so far about translations, transformations, and reflections. And we're going to put them all together to decide whether or not we have congruent figures, okay? These notes are going to be about 5 minutes. This is a very simple idea. It's not learning anything new. It's taking what we've already been doing, all of topic 6, translations, reflections, and rotations, and it's applying it to this idea of something being congruent, okay? So we talked about this already, but if you have a Tetris game, if you spin that blue piece or rotate it about the center, and if you translate it left and right, it's not going to change shape or size. So we know that if we rotate it and translate it and we drop it into place, it will fit because those transformations do not change the size and shape of a 2D figure. So pause the video, take a second to just write this little bit down. Those of you in class, I think you already have it. The 3 we have learned so far, translation, reflection, and rotations. The main thing I want you to remember is that everything, each shape, when it goes through this transformation, stays the same shape and size. Next week, we're going to get into transformations that actually change the shape and size. But the ones we've done so far, they stay the same. So if you know that congruent means the same, that's it. That's all you need to learn new for this 6-5. So if you'll go to our first example, everybody should have a highlighter. If you don't, grab one really quickly, because there's a couple of things I want you to highlight. Quickly, 30 seconds, get you a highlighter. If you borrow one of mine, just please make sure you bring it back. All right, the first thing I want you to highlight underneath example 1 is in this box right here. I want you to highlight the sentence, congruent figures have the same size and shape. And then if you see this little symbol right here, that also means congruent. Okay, the little equal sign with the squiggly line up top. That means same size, same shape. Okay. The other thing I want you to highlight, and it's basically saying the exact same thing. If you have 2 rugs that are the same size and same shape, that means they are congruent. So it's kind of looking at it from both directions. We know that if they're congruent, they're the same. We know that if they're the same, they're congruent. And so we're kind of back to this architect photo that we've been working with pretty much all of topic 6 so far. And the homeowner decides that they want a rug identical to the one in front of the couch over by the fireplace. And so to ensure the fact that it's the exact same size and shape, they want to use a sequence of transformations to make sure that when they get that rug over by the fireplace, it's the exact same size and shape. And so that's what they've done here. Okay, they have translated it over so many units, and then they rotated it clockwise, and then it guarantees, because all we did was a translation and a rotation, because those are 2 of the 2 that don't change the shape and size, we guarantee that the rug is the same size when it's over by the second rug is the same size over by the fireplace. Okay, not going to spend a whole lot of time on that. I do want to, however, you all are going to answer under try it, and everybody's going to have the right answer because we're going to do it together. How can you determine whether the orange and the blue rectangles are congruent? Okay, we've already said it. What would we do? Now, I'm not asking you to actually answer how many and what all you would do, but just in very general terms, how can you tell if 2 terms or if 2 shapes are congruent? Okay, and how do we test that? Using a what? You're right. Test it using a sequence of transformations to see if the first, I'll just say the orange, that's easier than putting the first. If the orange and blue are congruent. So you run a test. Can you do a sequence of transformations that would make the orange and the blue be right stacked on top of each other? If we can, that means they're congruent. If we can't, they're not. So if we label, this would be, and you guys are going to want to label this with me, P, Q, R, S. And since orange is obviously laying on its side, we're going to kind of flip it on its side, and we're going to call this P, Q, R, S, and these will be your primes. So we need to test, can we get the blue shaped quadrilateral translated, or I'm not translated, transformed, so either translated, rotated, or reflected, so that it lines up perfectly with the orange one? Well, the first thing we need is, let's see if we can't, if you think about this in the real world, if you have a box that's tall and a box that's long, what do you got to do to the tall box to get it to look like the other one? Lay it on its what? Yeah, lay it on its side. So the first thing we're going to do with our blue image is we're going to rotate it. Okay, we're going to rotate it counterclockwise 90 degrees so that the side PS becomes the bottom. So P is 1, 2, 3, 4, 5 boxes long. So 1, 2, 3, 4, 5 boxes long. So let's put a point here. We're rotating at about point S. So we're using point S as our rotation point, and we're just laying this box over on its side. So P gets laid over here, and then from P to Q, right? It's 1, 2, 3, 1, 2, 3, 4 boxes. So 1, 2, 3, 4 boxes. So this is where Q would go. And then we know that this right here would be R. So we've just laid this box on its side. And if it was 5 boxes tall, now it's got to be 5 boxes long. When it was 5 boxes or 4 boxes wide, we now know it has to be 4 boxes tall because we laid it on its side. Okay, everybody see that? Now, can we use a translation? And if so, what translation would slide that box exactly on top of the other one, lining up each point? Maddie?
Move them all 2 to the left.
And so 2 to the left would put Q here and P here. Then what? So let's write down what we've done so far. What do you know about how these figures relate? That's describing what we just did. So we had to rotate PQRS 90 degrees. Do I have to put counterclockwise? What could I do with 90 to make sure it says counterclockwise? Negative goes clockwise. Would I leave it positive? If I leave it positive, that means counterclockwise. So I don't have to actually write out counterclockwise. Rotate PQRS 90 degrees about point S. Because remember, that was our rotation point. We left point S right where it was. Then we translate two units left. Now, does that get us where we need? 2 units left, puts Q here and P here. Now what? 1, 2, 3, 4, 5 units down, now drops P right where it's supposed to be. So translate 2 units left and 5 units down. And we can say what? These two are what? Yeah, congruent. That's what we were trying to prove. So if it asks you how they relate, that means you need to describe the transformation, the sequence of transformations, and then decide yes or no if they're congruent or not based on your experiment or your test that you ran with sequence of translations. Okay? All right. So if you have a shape, it says, is quadrilateral ABCD congruent to QRST? Well, the first thing I'm going to do is what? Right before I even try to work this problem, what am I going to do? What do you think, Casey? Maddie? Oh, what do you think we're gonna do? Should I rename something to make this easier? Do I like A, B, C, D, and Q, R, S, T? Okay, let's rename these. So A comes first and Q comes first. So I'm going to make this Q and A. Okay, just to make it easier. B is next and R is next. So my R over here is really my B. I'm just renaming these to make it a whole lot easier for stuff to line up. My S comes next and my C comes next. So that means the S can also be called C. And my D and my T, so my inner angle D and my inner angle T line up. So I have renamed this. Now, hopefully it's a little bit easier. Yes. You can if you want. Remember I said, if you're kind of in the middle of the problem, if you want to mark them prime, you can. If you want to mark them prime at the end, you can do that as well. Okay, it's totally up to you. I'm just renaming them so that I know that A and A, B and B, D and D, all of those are going to line up. Okay, yes. Yes. So can I now try a few different things? And it doesn't matter if you reflect first or if you translate first, but in this example, they reflected first. The reason they reflected is because B's on the outside here and B's on the outside here, right? A and A stay the same, C and D stay the same, D stays in the middle. So that tells you that it's going to reflect. And that B is going to end up, think of the turtle, right? B was on this side and B is going to end up over on this side. So that tells you it's going to be reflection. Corbin, stand up. So the first thing they do is they reflect it. And I don't care what you reflect about. In this particular case, they reflected about X equals 1. And that's fine. They made X equals -1, their reflection point. Why is that super easy to do for point C? Does point C change if your reflection point is right on C? So that kind of makes it easy. C stays the same. D was 2 right here. See, D is 2 to the left. Now D is 2 to the right. So and obviously you won't be doing these on 2 separate graphs. So it'll be a whole lot easier to do. They're doing it in 2 steps here, which kind of makes it hard to see. Then you reflect A and you reflect B. And now you end up with this, right? And we've already said this is A, this is B, this is C, and this is D. So now you should be able to see that it's a simple translation to slide it, think A to A. Just pick one point. Make A line up with A. What's it take? It takes a translation 3 to the right and 2 down. And that drops your new A. Then with B, D, and C, you're going to do the same thing. You're going to translate them 3, 2, 3, 2, 3, 2. You're going to drop these new points. Now, were we able to get our original point dropped perfectly on our pre-image dropped perfectly on our image using translation, reflection, or rotation? Since the answer is yes, are these 2 images congruent? Yes, they are. So you just have to run the test and see if they can be mapped right on top of each other. You'll notice in this one, I like this B example because they do it all on one graph. They take ABC, and then they have JKL, which I don't love that, but they take it, and the first thing they do is they rotate JKL up. And when they do that, notice here, is there any way you can translate this to make these line up? Because C and C already line up. So you can't translate it because if you slide A and B, C is going to slide too. And you don't want C to slide because C already lines up perfectly. So are these 2 shapes congruent? No, they're not the same size. The black one is bigger than the green one. So they're not going to be congruent. And we proved it because we tried the sequence of transformations and it failed. If it fails the test, then they're not congruent. Okay, that's pretty much it. I'm not going to go into a whole lot more. What I want to tell you in class and anybody at home watching the video is I don't normally ask you to do this. It will take you about 5 minutes, so it's not that big of a deal. I want you to go to our Canvas homepage this weekend, and I want you to watch the little Savvis videos that I've linked. One's like 2.5, one's make 1.5 minutes. One is not even a video. It's just a quick thing you have to do. And then the other one is like 1.5 minutes again. I mean, this will take you 5 minutes. It's very short, but I think seeing the visual movement as opposed to trying to see it on your paper and visualize it in your own mind. I think seeing the visual movement will help. Okay. So I'm going to go ahead and stop the video and then I'm going to show you guys here in class what I'm talking about. So for you at home, watch the Savas videos, then do the Savas assignment and it's due on Monday.